mechanical operation. Okay guys, before starting the subject, we should know some background about this subject. Okay, what is the importance of this subject? So as far as chemical industries is concerned, any industrial chemical processes are especially designed to convert the raw material into product in economic and in optimized way, and in that sequence the material under consideration has to be passed through series of operations. It means if you want to convert the raw material into the product in any chemical industries, as I told you, the material under consideration has to be passed through series of processes, and that series of processes involves some physical changes as well as chemical changes. Are you getting a point? Once again listen, what again I am repeating, कि as far as any industrial chemical processes is concerned, they are especially designed to convert the raw material into product through sequence of processes, and those sequence of processes involves some physical changes as well as chemical changes. So the process that involved physical changes are called as unit operation, and the processes which involve the chemical changes are called as unit process. So you can say कि in chemical industries any material under consideration is going to be processed through the various steps, and those steps can be divided in two parts. One is the steps in which the physical changes takes place, and the step in which the chemical changes takes place. The any processes in which the physical change takes place called as unit operation, and any steps in which the chemical changes are involved, that is called as unit process. So what we should know first, in industrial chemical processes, not in, actually we should write the industrial chemical processes are designed to convert raw material efficiently into product through sequence of processes that involve physical and chemical changes, that involve physical and chemical changes of material under consideration, Clear? It means the material which has to be processed, it has to be passed through the series of steps. And those steps are physical changes are involved and some steps are chemical changes are involved. So my dear student, here I have told you the industrial chemical processes are designed to convert the raw material efficiently into the product through the sequence of processes that involves the physical changes and chemical changes of material under consideration. Clear? The unit involving physical change, the unit involving physical change of material, physical change of material called as unit process, unit operation. Clear है? Unit operation. So the unit in which the physical changes are involved called as unit operation, and the unit in which chemical changes are involved called as unit process. Please write down. The unit which involves the physical changes. First of all, just I am going to create the background of mechanical operation. And guys, mechanical operation is a part of unit operation, because in this unit the only physical changes are going to be involved. So the unit involving physical changes of the material is called as unit operations, and unit involving chemical changes of material called as unit process. Soeb, है तुम हो कि नहीं? तो you can say कि if you want to convert any material to product, then obviously it has to be passed through sequence of processes, and those sequences are subdivided into two parts: the unit in which physical change and chemical changes involves. Okay, so how can you further classify? It means total units involved in the chemical processes can be divided in two parts: unit operation and unit process. Okay. So in chemical industry there are two types of units are there. Means every material has to be passed through two types of units. One units where physical change, and other unit chemical change. Unit operation and unit process. Writing सही है कि नहीं है? Unit operation. Karthik, are you there? Shankar. Unit operation, unit process. Now I've told you physical changes are involved. Chemical changes are involved. As far as physical changes are involved, example of physical change involves are like heat transfer operation. Heat transfer operation is unit operation. Heat transfer operation. Mass transfer operation. Mass transfer operation. Mechanical Now it is clear. Okay, now so first of all I've told you ki in every chemical industries there are two types of units are there, in which one unit in which the physical change and chemical change. The example of the unit in which physical changes are involved, that is called as fluid flow operation, heat transfer operation, mass transfer operation, and mechanical operation. And the mechanical operation is the subject that we are going to start here, and that is the part under the unit operation in which only physical changes are going to be involved. Now at the same time, as far as unit process is concerned, the process in which the chemical changes are going to be involved, those units are called as like nitration process. Example of unit process are the nitration unit, nitration, ammoniation, etc. So in which chemical changes are going to be involved, like nitration, ammoniation, sulfonation. These units involve chemical changes. Is this clear? So first of all we should know that we are going to start the mechanical operation, and the mechanical operation is the subject that comes under the unit operation in which the physical changes are going to be involved. The question is that how the mechanical operation, or sometimes called as mechanical separation, is different from the mass transfer separation process. Because as far as separation process is concerned, in separation process obviously, as the name suggests, we are going to separate one component from the other component, from one phase to other phase. But how the mechanical separation, I will discuss. In mechanical operation, the one part is also called as mechanical separation. So in how the mechanical separation is different from the chemical separation, because in the mass transfer operation we are going to carry out the chemical separation. Chemical separation means like distillation, they are chemical separation. So as far name suggests, what is the basic difference in the mechanical separation and chemical separation? My dear student, in chemical separation, just like distillation, extraction, now we are going to use the mechanism of separation like solubility difference, or you can say vapor pressure difference, like that. But in mechanical separation, as far as mechanical separation is concerned, in this separation we are going to use the mechanical forces. Either it is small in magnitude or large in magnitude, that is different thing, but we are going to use the mechanical forces. What are the mechanical forces? Mechanical forces like gravitational forces, like centrifugal forces. These are the mechanical forces. Means we are going to separate the one species from the other species with the help of mechanical forces. Okay, while in chemical separation, just like in the mass transfer operation like distillation, like extraction, in these types of separation processes we are going to use the mechanism like vapor pressure difference, or you can say volatility difference, or you can say solubility difference. Okay, I will increase the thickness. Yes, is this clear? First of all tell me, is this clear? So first of all we have started the subject with the basics, and basic is what I told you. Once again I am repeating, the every material under the process has to be passed through different units. We can subdivide the units into two parts: unit operation, unit process, and the mechanical operation is a part of unit operation in which the physical changes are going to be involved. Now I am going to be more specific for mechanical operation subject. Now the subject is here mechanical operation. How can you define the subject mechanical operation? First of all, this is the subject that deals with the particles. This is the subject mechanical operation. How heat transfer is unit operation? Sir, in the heat transfer we are only change the phase, or we are going to only transfer the heat. There is no chemical change are involved. That's why it is a unit operation. Like evaporator is a unit operation, heat exchanger is a unit operation, because in the heat exchanger you are going to transfer the energy from the hot fluid to the cold fluid. Hot fluid is losing its energy and cold fluid is attaining or gaining the energy from the hot fluid. So there is no chemical changes, only physical changes are going to involve, na? That's why it is a now. So first of all, as far as mechanical operation is concerned, mechanical operation subject deals with the ये mouse कहाँ से आ गया? Mechanical operation is the subject that deals with the study of the particles, and not only study, it involves the handling, processing, characterization, conversion and application of wide variety of particulate materials. Is this clear? Now, so as far as definition is concerned, how can you define the mechanical operation? So you can define the mechanical operation is the branch of science and engineering, or you can say it is a part of unit operation that deals with the handling, processing, characterization, conversion and application of different varieties of the particulate materials. Now the question is, what is the particulate materials? As far as particulate material is concerned, the wide varieties of the material is called as particulate materials. Okay, so it is a branch of branch of science and engineering, branch of science and engineering that deals with the processing, comma, handling, comma, characterization, conversion and application of wide variety of particulate materials. Please write. So sir, mechanical operation is the branch of science and engineering that deals with the processing, the very important term, processing, handling, characterization, conversion and application of wide varieties of the particulate materials or particulate materials. Now what is meaning of processing? One by one we should know. What is meaning of processing? Anyone? What is meaning of processing? What do you know about processing of particulate material? As far as processing is concerned, my dear student, if you are going to process, it means if you are going to crush, if you are going to change the size by some process like crushing, grinding, attrition, rubbing, where different processing action, if you are going to change the sizes or shapes, these are called as processing. So these subjects involve processing of the material. It means it's just like changing the size and shapes. Now what is meaning of handling? Handling means just transportation, how we are going to handle it, because success and failure, because my dear student, I would like to say you ki around 45% of the chemical products are in solid form. 45%, nearly 45% of the chemical products or in the solid form. So it is also very important how we are going to handle this, okay, how we are going to transport these, because it is very difficult to transport the solid as compared to liquids. Okay, that's why it is very important to know the handling, how we should handle the particulate material. Now, what is the meaning of characterization? As far as characterization is concerned, just to introduction, suppose if I've told you how can you characterize yourself, then obviously you can characterize yourself by your height, by your weight, by your nature. Similarly, we can also characterize the particulate material on the behalf of its sizes, its shapes. So that is called as characterizations. It means just like some properties like density, we can characterize the particles or particulate materials on the behalf of their sizes, their shapes, their densities, etc. So this is called as characterization. Yes, obviously, how we can store, how can you handle, these all are the part of handling properties, handling of the particulate material. As I told you, nearly 45% of the chemical products are in the particulate form, and that's why it is very important to emphasize how we can handle this, how can you transport these materials, these products. It is also very important, and these all study of handling will come under the subject mechanical operation. As far as characterization is concerned, characterization means just to characterize the particles. We can characterize the particles on the behalf of its size, its shape, its density, etc. That is called as characterization. As far as conversion is concerned, if the particulate material undergoes some chemical reactions, if particulate material undergoes chemical reaction, for example, in the catalyst, as you know, the catalysts are used to increase the rate of reaction. Okay, and that is only possible because it provides the large surface area in unit volume. So as far as conversion is concerned, if any particular material undergoes chemical reaction, then how much conversion of the raw material into product, it is the part of conversion. Clear hai? Yes. Now, as far as application is concerned, now what are the applications of this particular material? It is also the part of mechanical operation. So as far as overview of this subject is concerned, we can define the mechanical operation. It is a branch of science and engineering that deals with the handling, processing. I have discussed one by one already. My dear student, processing means, processing means just to change the sizes. Handling means how we are going to handle, how we are going to transport the particular material. Now, characterization means characterization of the particular material is by sizes and shapes and densities, and obviously conversion and application. These all are the part of mechanical operation. Now it is clear to you? Mechanical operation. My dear student, I would like to say you, around 75% of the chemical manufacturing processes involves small solid particles or fine particles, and proper design and handling and transportation of those fine particles are playing very important role in the success and failure of the industries. Is this clear? Once again listen, I have told you around 75% of the chemical manufacturing processes involves small solid particles, or you can say fine particles, and that's why it is very important to have a proper design and handling of the fine particles, and that is the reason why it makes a very large difference in the success and failure. So if you are much more concerned about the success and failure of the industries, if you are much more concerned about the success and failure of the industries, then you should be very, very concerned about the handling characteristics, transportation characteristics. Their characterizations are very important. Clear? Now, if any problem up to this point, you can ask me. So this is the sub definition is clear. If any doubt up to this point, you can ask. Now characterization of solid particles. हेडिंग इज कैरेक्टराइजेशन ऑफ सॉलिड पार्टिकल्स. केमिकल रिएक्शन में कोई, मैंने क्या बोला, कैटलिस्ट जो है केमिकल रिएक्शन में इन्वॉल्व नहीं होता है सर. मिस्टर अम्ब्रिकेश मिश्रा, हेयर कन्वर्जन मीन्स, as I told you, catalyst does not involve in reaction. Catalyst only provide the surface area to fasten the chemical rate of chemical reaction. So there is also role of solid particles now in conversion. First of all, here a role of solid particles in conversion is concerned. There is a role of catalyst actually. Now come to the characterization of the solid particles. As I have told you, if I have told you just characterize yourself, or you can characterize by your weight, your size, your walking style, your laughing style, etc. Similarly, we can also characterize the solid particles by its size, by its shape and density. Solid particles can be characterized by shape, size and density. As far as density is concerned, size, shape and density. Now what is density actually, my dear student? If we have a homogeneous solid, if we are going to break the homogeneous solid, now as far as size, shape and density, as far as density is concerned, my dear student, if you are going to consider the homogeneous group of solid particles, in homogeneous group of solid particles, if you are going to break the homogeneous solid particles, then density of each solid particles will be same. But if you are going to consider the non-homogeneous solid particles, just like ores of iron, in that case if you are going to break this, then different particles have different densities. So that's why the density will also play important role in the characterization of the solid particles of non-homogeneous solid. In homogeneous solid, density is same for every particles that combines the homogeneous solid. Now as far as shape and size is concerned, these two are very important characterization features of the solid particles. So first of all, size and shape, and this size and shape, these two terms are interrelated to each other. Size and shapes are interrelated to each other. Listen sir, very good Pawan. As far as size and shape is concerned, size and shape are interrelated to each other. Why interrelate? Because we are not supposed to, we are not assumed to size without considering, without imagining shape of the particle, because size is only going to be, so for example, if I am going to say कि length of this cylinder is 10 centimeter, then if I am going to take length is 10 centimeter, it is size, then obviously first of all, before considering the length 10 centimeter, there should be a imagination about the shape, what is the shape of the cylinder. So that's why I am telling you कि size and shapes are interrelated to each other. Okay, without considering the shape, without imagining the shape of the particles, we are not supposed to define the size. Clear? So size and shapes are interrelated to each other. So first of all, we should know the size. So I am going to start sizes, then I will start the shapes. So first of all, start the size, particle size. Particle size, my dear student, it is very important as it affects the properties such as surface area per unit volume. Particle size. So particle size is very important features, and obviously we know it will affect the surface area per unit volume. If large size particles are there, then obviously it involves less surface area in given volume. But if you're going to crush it, if you're going to crush it in small sizes, if you're going to break into small sizes, then obviously it will increase the surface area in unit volume. Okay, and that is going to happen in the catalyst. Obviously in the catalyst, the particles are going to be break in very small sizes like micron, angstrom sometimes. Now, so that's why the particle size is very important, because it will affect the surface area per unit volume. How much surface area is there in unit volume? Yes, very good, Anurag. If you are going to specify the sizes of the particles, then we have to make the assumption about the shape. It's very important. Okay, so as far as particle size is concerned, particle size is very important because it will affect the surface area in unit volume. If a large size particle is there, that large size particle have less surface area, a small surface area, as compared to smaller size particles if you are going to break into small sizes. So that's why it is very important features. But the question is that how can you define the particle sizes? So there are different persons have given their own opinion about the particle sizes, because it is very easy to define the particle sizes for the regular shapes particles. For regular particles, two types of particles are there. One is called as regular and irregular. Listen, regular particles are the particles just like a sphere, cylinder, cube. They are regular particles, but in real applications the particles are of irregular shapes. Those are called as irregular particles, and for irregular particles it is very difficult to define the sizes. We can define, and at the same time we should also know, to define the sizes there are some particles are there which require only one parameter. Some particles are there which require only one parameter to define the sizes. For example, a sphere. In the sphere, only one parameter is sufficient to define the sizes. For example, it is only diameter or radius. In the case of cylinder, two parameters are required: length and diameter. Now, similarly in the cube, again one parameter is required to define the sizes. In cuboid, three parameters should be required: length, width and height. So that's why we should know there are some regular particles are there and some irregular particles are there. In regular particles, some particles are there which require only one parameter to define the sizes. For example, in a sphere, only one parameter is sufficient, it is diameter or radius. In cylinder, two parameter, length and diameter. In cube, only one parameter. In cuboid, three parameters are required. So that is different thing, but at the same time it is very important, because in real applications the particles have no definite sizes and shapes. They are irregular, that's why they are called as irregular shapes. The question is that how can you define the sizes of the irregular particles? The major concern about the sizes is of the irregular, not for regular. Yes, I am discussing here surface area per unit volume, not only surface area. You should be very clear about this. I told you that particle sizes are very important because it affects the surface area per unit volume. In unit volume, large surface area is there. If you have, for example, if you have any particles in this shape, now here its volume is definite. If you are going to break these particles into smaller sizes, then obviously it will increase the surface area, and if surface area will increases, then obviously rate of mass transfer will increases. And the same thing you have seen in the leaching. In the leaching, the first side particles are going to be crushed. Okay, so there are different applications are there. If you are going to break into the smaller particles by processing some process, then obviously we are going to increase the surface area for the process to take place in unit volume. Okay, so don't confuse. Now, so once again, my dear student, what I told you, it is very easy to define the size of the regular particles as compared to irregular particles, but we are going to more concerned about the sizes of irregular particles. Then how can you define the size of irregular particles? Initially, in initial days, like in 1931, Martins are there. One person is Martin. So Martin has given its own view about the sizes of irregular particles. One is called as ferret. So as far as, first of all, you should know, in particle size, it is very important. It is very important because affect the surface area per unit volume. Okay. For regular particles, sizes can be easily defined. But for irregular particles, can be easily defined. For regular particles, sizes can be easily defined, but for irregular particles, not. Mr. Divakar, shape is defined by sphericity, not size. You should be very clear. A sphericity term is only for defining the shape, not sizes. I am here discussing about the sizes. For regular particles, sizes can be easily defined, but for irregular particles, sizes are defined in various ways. First is Martin, first defined by Martin in 1931. Although it is not going to be used, but still Martin and others call as Ferret. What Martin says, Martin defined the size of an irregular particles as the length of the line bisecting the maximum cross-sectional area of the particle. Martin has defined the size of irregular shapes. Martin defined the sizes of irregular particles or shape as the length of the line as length of line bisecting the maximum cross-sectional area, bisecting the maximum cross-sectional area. Please write Martin defined the size of an irregular particle as the length of the line bisecting the maximum cross-sectional area of the particle. What does it mean? Listen. Martin said that if you want to define the size of an irregular particles, then what we should do first, you should expose the particle, you should place the particles so that maximum cross-sectional area should be there. For example, let's say if this is the any particle, okay, you have this particle, it is irregular particle, and if you want to define the size, then Ferret told it is defined as the length of the line which bisect the maximum cross-sectional area of the particle. As my student, now this is the cross-sectional area. If you see, this is the cross-sectional area of the particles. So first of all, in this case, length of any line which bisects, suppose this area, whole area I am going to bisect by this line, let's say like here, this is, or do sorry, ये तो दिल बन गया, like this here. Let's say this is the cross-sectional area is here. Now if this is the line which bisect the total cross-sectional area into two equal parts, so this length is called as Ferret length, Martin's length. Then Martin has defined the size of this particle as the line length of the line which bisect it means if any line which divides the total cross sectional area into two equal parts, that length of the line is called as Martin diameter. Okay, Martin length you can say. Clear hai? Yes or no? So Martin length, Martin diameter, or you can say Martin length, no issue here. So Martin length, Martin has suggested that if you want to calculate the sizes of the irregular particles, that is defined as the length of the line which bisect the maximum cross sectional area of the particle. Okay, now at the same time there is one more person was there who has also defined the size of irregular particle, that is called as ferret. F-E-R-E-T-S, ferret's diameter. Ferret's diameter, F-E-R-E-T, ferret. Please write ferret diameter. According to ferret diameter, it defines the particle size as distance between the two most extreme point on the particle surface. Is defined as, ferret diameter is defined as, ferret diameter defined as, or define particle sizes, define particle size as distance between two most, distance between two most, distance between two most extreme point on the particle surface. Extreme point on particles surface. It means again the same kahani is here, same story is also here. Let's say you have any particles like that. So what is, if you are going to expose the particles in such a way that maximum cross sectional area is available, so distance between two extreme point, this is the two extreme length, these two extreme points are there, then length of this is called as ferret diameter. So ferret has defined the size of an irregular particles as, Harsa, what happened? Bisecting maximum cross area मतलब जो भी maximum cross section area होगा उसको bisect कर दो. Means you have to expose the particles such that maximum cross area, because particles are 3D in shape na, particles are 3D in shape, so you should place the particles such that maximum cross section area is going to be observed. Are you getting a point? For example, let's say how can I give you example? Let's say this is the mouse is here, and in this mouse it is 3D shape is there. Here if you are going to expose in this way, then here the cross section area is less, but if you are going to place in this way, then here the maximum cross section area is available. So you should place the object such that maximum cross section area is going to be observed, and then you can have a line, you should have a line which bisect the maximum cross section area. That line is called as Martin diameter. And in the ferret diameter is concerned, in the ferret diameter again you should place the object such that maximum cross sectional area of that particle is going to be observed, and the length, two extreme length between two extreme points on that maximum cross sectional area is called as ferret diameter. Now it is clear? Yes or no? Mr. Harsa, are you getting a point? As far as what is meaning of maximum cross sectional area, as I told you, if you have any particles, any irregular particles, then its orientation is very important. Some orientation have less cross sectional area and some orientation may have maximum cross sectional area. So you should place first object in such a way that its maximum cross sectional area is exposed to you, okay, and then you should have a line which bisect the maximum cross sectional area into two equal parts. That length is called as Martin diameter. Now as far as ferret diameter is concerned, again the same particle you had to be exposed in such a way that maximum cross sectional area is going to be exposed or observed, then the length between two extreme point on that is called as ferrite diameter. Now it is clear? Yes. First of all, you should orient the particles in a such a way that maximum cross-sectional area is going to be viewed. Then any line which bisect the maximum cross-sectional area into two equal parts bisect, then the length of that line is called as Martin, and the length on two extreme points on that maximum cross-sectional area is called as ferrite. Clear hai? Now at the same time, you should know what are the drawbacks of Martin and ferrite diameter. Anyone? What drawback is there in calculating the sizes by the Martin and ferrite? Anyone? My dear student, if you will see, let's say this is the particles. Here these are two extreme points, that is called as, this length is called as ferrite diameter. Length between two extreme point here, these two extreme points are there, ferrite diameter. And as far as Martin diameter is concerned, I told you that the length which bisects, this is called as Martin diameter. Martin diameter here. Okay, so here ferrite and here Martin. What drawback is there? As far as drawback is concerned, my student, you will observe that even if this point and this point is fixed here, but if you are going to change the shapes, for example, if you have a different particles having same maximum cross-sectional area, but if its shapes are going to be changed like that, still it will indicate the same sizes. Am I right? Yes or no? You can say, my student, I told you, if thickness, you can say in this way, if the thickness here, let's say thickness is 1 mm, if thickness of this particle is 1 mm, and if thickness of particle has been increased to 2 mm, if thickness of the particle is going to be changed keeping same maximum cross-sectional area, shape is same here, but thickness is going to be increased continuously, but still what happened? Still it will indicate the same sizes. Am I right? Yes or no? For the different shape, it will indicate the same size if the two extreme points are going to be fixed, or if the maximum cross-sectional area is exposed is same, but if thickness of the particles are going to be changed, increased, still it will indicate, although by changing thickness its size should be changed, but it will indicate the same size. Is this clear? Yes or no? Guys, is this clear? If thickness of the particles are going to be changed, if thickness of the particles, Pallav, are you there? If you are going to increase the thickness of the particle keeping same cross-sectional area and same end points, still the ferrite and Martin diameter will be unchanged. That is a drawback. Martin and ferrite diameter both are based on the maximum cross-sectional area. In both cases, we have to expose the particles towards maximum cross-sectional area. Then as far as ferrite is concerned, in the ferrite we have to calculate when the particles has to be exposed. In the both cases, we have to expose the particles through maximum cross-sectional area, towards the side of maximum cross-sectional area. Then as far as ferrite is concerned, in the ferrite the length between two extreme points of those particles are called as ferrite, and the length of the line which bisect the maximum cross-sectional area is called as Martin. But the drawback of the both diameter is concerned, as far as सर मार्टिन साइज कैसे चेंज होगा मिस्टर राजकुमार? मिस्टर राजकुमार, इफ यू हैव दिस पार्टिकल्स एंड इसकी कुछ थिकनेस अलग है, हम थिकनेस को बढ़ाते जा रहे हैं, इधर आपके पास तो केवल ये एरिया है ना, यू आर गोइंग टू ओनली मेजर ऑन द बिहाफ ऑफ दिस थिकनेस, कुछ भी बढ़ाते जाओ इधर, क्या मतलब है? थिकनेस यहाँ इंक्रीज करते जाओ, यू कैन इंक्रीज थिकनेस ऑफ दिस, बट इफ यू आर गोइंग टू कंसिडर दिस मैक्सिमम क्रॉस एरिया, देन ओनली दिस इज कॉल्ड एज Martin and ferrite. It will not be affect if you are going to increase thickness of the particles. I told you it is not exact result, it will give you approximate results. All length will be nearly the same, nearly same. It is not exact results. That's why I am to tell you there are various drawbacks are there. Sir, two extreme point, not tangent sir, tangent नहीं होगा, extreme point होगा, बात को समझिए, two extreme point. Now, so that is drawback of ferrites and Martin diameter. और ये एरिया क्या इक्वल है आपका एक रेक्टेंगल में, तो दैट इज ड्रॉबैक. and that's why we can't use the Ferret and Martin diameter in application. Sir, sir, in this case I told you you can use, अगर दो है दोनों का एवरेज ले लो, समझ गए? ये कोई, ये इन्होंने अपना सजेशन दिया, बट I told you they are not going to use in applications because there are wide varieties of drawbacks are there. Otherwise, there is one more rule is there. You can take the average of two maximum length. You can take the average of two maximum length. It can also be defined the size of the particles. There are various ways are there. They are just approximate. Here in this case, if you are going to increase the thickness, let's say it is the thickness of the particle. If we are going to increase thickness of this particle from 1 mm to 2 mm, still what happen? The Ferret diameter and Martin diameter is same. अरे मिस्टर सोएब, मैं रिपीट कर रहा हूँ. आप ये बताओ सर, ये बुक है, ये बुक है, इसका मैंने मैक्सिमम क्रॉस एरिया ये ले लिया. अब ये बताओ इसकी थिकनेस को आप बढ़ाते जाओ. यू कैन इंक्रीज थिकनेस. नाउ यू कैन इंक्रीज थिकनेस हियर. नाउ स्टिल if you are going to define the cross section, if you are going to define the size by its two extremist point, then it is going to be changed. Let me know. Either you can increase thickness or decrease, increase thickness or decrease thickness. Still, its Ferret diameter and Martin diameter is same. Are you getting a point? Mr. अंकित, आप बता रहे हो या पूछ रहे हो? पहले ये बता दो आप खुद सोचो कैसे चेंज होगा. सर ये पार्टिकल आपके पास है, इसकी थिकनेस अभी ये है, अभी थिकनेस हमने इंक्रीज कर दिया. नाउ इज इट गोइंग टू बी चेंज द मार्टिन एंड फेरेट? ओके, क्लियर. So but again the drawback is there, that's why we are not going to use this. The question is if Martin and Ferret is also going to. भाई मेरे समझ नहीं आ रहा ऐसा भी क्या डाउट आ गया इसमें यार. क्या पूछ रहे हो भाई? साहिल के ऊपर डाउट क्लियर करना. तो ये दिक्कत इसी आया, इसलिए मार्केट में आया, इसलिए क्योंकि तुम एवरेज ले सकते हो, अप्रॉक्सीमेट ले सकते हो अगर लेना हो तो. कुछ पार्टिकल्स के लिए तो सही होगा ना. नाउ then again the problem is still there कि how can you define the size, accurate size of the particles. My dear student, although Ferret and Martin diameter is there, but it is not going to be used in all cases, only some certain cases. Drawback का मतलब ये नहीं कि वो गलत है. Drawback का मतलब ये बात कि they are not going to use, they are not able to use in all cases. Now the next thing is that the simplest shape of the particle is what? The simplest shape. इसमें इतना दिमाग लगाने की जरूरत नहीं है. The simplest shape of particle is a sphere. The simplest shape of the particle is sphere. Yes. Why? Because of its symmetry. Because of its symmetry. Because particles looks the same from whatever direction you want to view. My dear student, simplest shape of the particle is sphere because of its symmetry, and it looks like exactly the same from whatever direction it is going to be viewed, and behaves in the same manner in a fluid irrespective of orientation. So why it is simplest shape? Because of its symmetry. It means you can't question about its orientation. From any direction, if you are going to view, it looks like the same, and its behavior is not going to be affected if you are going to process the spherical particles in fluid. Its behavior will be same because orientation of this particle will not off. Is this clear? So first of all, the simplest shape of the particle is sphere because of its orientation, because of its symmetry. It means from any direction, if you are going to view, its look exactly the same, and its behavior is not going to be a change when it is going to be treated in a fluid because of its symmetry. Clear hai? Yes or no? And that is the reason why these spherical particles are going to be considered as a reference. That's why the spherical particles are going to be considered as a reference particle. And if you want to define the sizes of the irregular particles, then sizes of the irregular particles are going to be defined in form of the size of equivalent sphere. It is very important, size of equivalent sphere. So my dear student, as I told you, कि Martin and Ferret diameter Mr. Ankit Saraswat, cube is symmetrical. हर एक एंगल से, from all angle the cube is look like the same. From all angle, from top it will look like a rectangle, from side it will look like a rectangle. Okay, but from one angle, from all angles, from all angle, is the cube is going to be look like the same? Corner view से, corner से देखो कैसा दिखाई देगा आपको, from corner. Okay, that's why guys, the sizes of, please write down, as I told you कि Martin and Ferret diameter is failed. That's why we are going to define the sizes of irregular particles in terms of equivalent sizes of a sphere. Please write down here. The size of irregular particles is defined in form of size of an equivalent sphere. Size of an equivalent, a very very important term, size of an equivalent sphere. What is meaning of size of equivalent sphere? Size of an equivalent sphere means, now we are going to define the size of an irregular particles in form of size of an equivalent sphere. As the name suggests, it should be compared with the size of a sphere. Every sizes of an irregular particle should be defined in terms of equivalence of a sphere, size of equivalent sphere. What is meaning of equivalency here? What is meaning of equivalency? The term equivalent means what? Anyone? What is meaning of equivalency here? Size of equivalent sphere. The one term is there, equivalent. What is meaning of equivalent? Equivalent in what sense? Equivalent in height, equivalent in weight, equivalent in surface area, equivalent in volume, equivalent in surface to volume ratio, equivalent in mass. We are going to talk about equivalence, but in what sense it is equivalent? Sir, equivalence of size means the diameter that assigned to an irregular, as I told you, the size of an equivalent sphere. It means the size of an irregular particles we are going to compare in terms of size of an equivalent sphere. It means you have an sphere which is equivalent to any irregular particles, but it is equivalent to sphere for what? First of all, try to listen what is meaning for this. Just break this language, break this sentence into the different parts. First of all, here size of an irregular particles is defined in form of size of an equivalent sphere. So first of all, an sphere size is only going to define by diameter or radius. Am I right? As I told you, कि sphere require only one parameter to define its size, and that is called as diameter or radius. So as far as irregular, it is any irregular particle you have, and if you want to define the size of this irregular particles, that size of an irregular particles we can define in terms of size of an equivalent. This sphere is equivalent to this particle, but equivalent in what sense, my dear student? This sphere may be equivalent to this particles in terms of volume, maybe in terms of surface area, maybe equivalent in terms of surface to volume ratio, maybe equivalent to in terms of volume to surface ratio, maybe in equivalent to equal terminal settling velocity. It depends upon the different process condition. Are you getting my point? Yes or no? Let's say for a moment, if we are going to say that this sphere is equivalent to this irregular particles in terms of volume, it means volume of this particle is same as volume of this sphere, then whatever the diameter is there, this diameter is called as size of that irregular particles. Am I right? But this is the size of irregular particles in terms of equating the volume. Am I right? And that is called as volume diameter. So different types of sizes are there, my dear student. It is very important. Different types of sizes are there. Different types of sizes are there. So we can define the different size of an equivalent particles. As far as size of an equivalent sphere is concerned, the equivalency, it means some properties must be same. And what property must be same here? If we are going to equate the property as a volume, if we are going to equate the property of volume, means volume of this particle, this irregular particle is going to be same as volume of this sphere. So whatever the diameter of this particle, this sphere is concerned, that is called as size of this particle in equivalence of volume, called as volume diameter. Sometimes, now here, let's say it is again here, it is irregular particles, and here it is sphere. Now if surface area of this particle is same as surface area of this sphere, then whatever diameter is there, that is called as ds, surface diameter. Are you getting the point? This is called a surface diameter. Is this clear? Yes or no? So first of all, the term equivalent of the size means what? Equivalent of the size means the diameter that assigned to an irregular shaped particle is same diameter as that of a sphere which behaves identically when both are exposed to the same process. It means this sphere and this irregular particle is behaving same when the both particles are exposed to the same process. That's why they are equivalent. Am I right? Yes or no? So equivalency, it is very important to clear the term equivalency. Equivalency in what? If I am equivalent to you, it means in what sense we are equivalent? In weight or in behavior or in other terminologies. That is very important. That's why here, my dear student, I would like to clear it. Equivalent of the size means the size the diameter which we are going to assign to an irregular particles is the same diameter as of this sphere. Means diameter of this particle or size of this particle is same as diameter of this sphere when both the particles are exposed to the same environment. They will behave as the same. Clear? Is this clear? Yes or no? So not only volume we can equate now, but it is also very important if you are going to equate the volume for the given density, my dear student, if you are going to equate the volume for the given density, or if you are going to equate the mass for a given density, it means volume is also same. My dear student, I would like to ask you, if you have a two different shapes particle is there, one is sphere and other is irregular particles. Just try to understand here. Let's say one particle is irregular and other particle is sphere. Now its mass is same here. Mass of this particle is same as mass of this particle. Mass of 1 equal to mass of 2. Now, and they are made of same material. Okay. Now density is same here. Their density are same, my dear student. Their terminal settling velocity will be same or different. Their terminal settling velocity will be same or different. As terminal settling velocity is concerned, ut, I will discuss in the later on, but just use your common sense. Terminal settling velocity means the velocity which they are going to be attained when there is no acceleration is there. So if their masses are same and density are same, and if both particles are going to be allowed to fall down in the same environment like air, their terminal settling velocity is found to be same or different. How many of you are going to say it will be same? Sir, you should be very careful. You people have only remember ut equal to g dp square rho p minus rho. That's why this is the biggest problem of you people. That is only for sphere. Do you know? That is only for sphere. Do you know? Yes or no? This formula is only for sphere. Sir, you should know the basics, because you people always remember the final formula, and I am totally against of this. You should not remember the final formula. It is only for spherical shapes, not for all shapes. Sir, as far as balance is concerned, if you are going to apply the balance, the only two forces is going to act here. One is mg, and here drag force, and here buoyant force. Am I right? Yes or no? At the condition of, just I am going to tell you the basics of this. No need to write, just try to understand here. Now, net force will be 0 when the terminal settling velocity is going to be attained. And as far as net force is 0, this should be mg, mass of the particle. This should be balanced by drag force plus buoyant force. Sir, mg drag force is just like what? Cd by 2 into rho into u square. U is the velocity, relative velocity of the particles. Now, into AP, projected area. Okay. Now, as far as buoyancy force is concerned, buoyancy force is always going to be exerted on the volume of immersed object, and the volume of the immersed object is here V, total volume, into rho of the fluid into G. Am I right? Now here in this case, my dear student, sir, listen. What is the projected area? Sir, it is possible, na? It may possible that projected area may be same, because projected area is frontal area. Projected area is frontal area. May be possible that this area is going to be observed from the front view. If you are going to observe, may be possible the projected area is same here. It will not affect 2. Sir, listen. In this case, if mass is same here, then terminal settling velocity is going to be same, because density I told you is same, then volume will also be same. Then the terminal settling velocity is not going to be affected too. Yes, volume displaced, and volume displaced is the volume of the object itself, and the volume of the object, I told you, since density is fixed there, I told you already, density of the two particles is same here, then mass is same. Sir, these forces are not going to affect too much. They are nearly same. अभी तक तो नाउ माय डियर स्टूडेंट, अभी तक तो आप बात कर रहे थे डेंसिटी की, बात कर रहे थे, साइज की बात कर रहे थे. अब बात कर रहे हो आप ड्रैग फोर्स पे आ गए, ड्रैग कोएफिशिएंट पे आ गए. Sir, problem is that you people are always going to remember the final formula. You don't know where we have to use and where we have not used. Mr. Shankar, you should know dv by dt is 0 because there is no acceleration. Sir, in terminal settling velocity, Mr. Shankar, you should know that there should be no any acceleration. There should be velocity, but there should be no acceleration. Is this clear? Yes or no? So, my dear student, if the two different sizes of the particles are there, but they have different same mass, and density is same, then volume is same, then their terminal settling velocity is nearly same. Clear hai? So listen, as I told you, what is my objective? My objective to discuss equivalency. So equivalency in the sense of what? If we are going to discuss about the equivalency in terms of mass, then the or volume, the volume of the particle must be same. Now, the please write here, as I told you, is size of an irregular particles is defined in form of size of an equivalent sphere. So please write here, equivalence of size means equivalence of size means, please write down, equivalence of size means that the diameter, that Pawan Yadav, is this clear? The diameter assigned to an irregular, diameter assigned to an irregular particle, diameter assigned to an irregular particle is the same diameter, means what diameter we have assigned, what size we have assigned to irregular particle is same as diameter of a sphere, is same as dia of that sphere, dia of that sphere, which behaves identically when both are exposed to the same condition. When both are exposed to the same process. Clear है? So whatever size we have assigned, whatever diameter we have assigned to an irregular shape will be same as diameter of the particle, diameter of spherical particles, which behaves identically when both are exposed to the same process. Behavior should be identical. So characteristic features should be, which behavior should be identical? Not all behavior. It is very important. Behaves identically. Identically in what sense? It is very important. First of all, listen right here. Equivalence of size means the diameter that assigned to an irregular particles is the same as diameter of the sphere that behaves identically with when both are exposed to the same process. Means behavior should be identical. So my dear student, we can define the particles of irregular shape through different size of the different diameter of the spherical particle. So we can define the particles, same particles can be defined with different size of spherical particles. Do you know? Thank you, Soeb. Let's say any irregular particle is there. The same irregular particles we can define in different sizes of sphere, different sizes of spheres. Do you know? Yes or no? You can draw this figure here. What it means here? Let's say any irregular shape particle is there, we can define in different sizes of sphere. Why? Here 1 2 3 4 5 different diameter of sphere is there. So we can define the single irregular particles with different size of spheres, and they are equivalent. This spherical particles is equivalent to this spherical particle in some property. So what equivalency is there? There may be equivalency of volume, there may be equivalency of, it depends upon what we are going to equate. Is this clear? A single irregular particles can be defined in different diameter of the spherical particles. Different diameter of spherical particles. They are spherical particles of different diameters. Different diameters. Are you getting my point? So a single irregular particles can be defined in terms of different diameter of the spherical particles, depends upon what property we have selected to equate. What property we have selected to equate. लो एडवांस फीचर का हमने यूज कर रहे हैं. लो So different sizes of spherical particles can be there for the single irregular particles depending upon what properties we are going to equate. Yes, very good. So please write down here. Although, please write down. Then I will complete this figure. Although the particle is represented by represented although the particle is represented by a sphere of different sizes, by a sphere of different sizes depending upon the property selected. कौन सी प्रॉपर्टी हमने सेलेक्ट किया है इक्वेट करने के लिए? क्या इक्वेट करने के लिए? Equate, we are equating the volume or surface area or surface to volume. What we are going to equate depending upon that property selected. Please write down. Although the particles is represented by the shapes of different sizes, sphere of different sizes depending upon the property selected. Now is this clear? It is irregular shape. So what different sizes of spheres are there for single irregular particles? I am going to discuss here. Is this clear? Yes or no? They are equivalent spheres. They are equivalent spheres for an irregular particles. Please note some of them are as below. Some of important diameter of sphere for an irregular particles are as below. First point is the sphere of the same volume as the particle. The sphere of same volume as of particle. Here we are going to equate the volume. Second, the sphere of same surface area as of particle. Third, the sphere of same surface to volume ratio, same surface to volume ratio of particle. Clear है? And etc. So we are going to define here first volume diameter, please define, and etc. so on. First we are going to define here, please write volume diameter dV. What is volume diameter, anyone? The volume diameter is the diameter of the equivalent sphere of an irregular particles which we have obtained by equating the anyone. What is volume diameter? It is diameter of the sphere. It is diameter of a sphere dV, diameter of the sphere of the same volume as of the particle. Very good. Same volume as particle, call as volume diameter. Call as volume diameter. Diameter of the sphere of the same volume as a particle. How can you calculate the volume diameter? So my dear student, if you have irregular particles, just try to understand here. If you have an irregular particles, and if you are going to equivalent sphere is here, and here if the volume of this particle is same as volume of the sphere, then whatever the size of this particle is there, that sphere is called as dV. How can you find out this? It is very simple. If you want to find the dV, you should equate the volume. So how can you equate the volume? Volume of the particle, let's say Vp is there, and Vs is what? Volume of the sphere, and the volume of sphere is pi by 6 into dV cube here. And why dV? Because we have equated the volume, that's why it's called volume diameter. Then we can calculate the dV as 6 into Vp upon pi whole power 1 by 3. This is called as volume diameter. Any problem? So this is called as volume diameter. Very good. So as you have drawn this figure, my dear student, this, let's say this is called as dV, volume diameter. So this is the diameter of, this is diameter of the equivalent sphere. It is diameter of the sphere of this irregular particles when we have equated the property of volume. So first I've told you different sizes of the sphere we can obtain for the single irregular particles depending upon what property we are going to equate. If you are going to equate the volume of this irregular particle is the volume of the sphere, then this corresponding diameter of the sphere is called as volume diameter, and this is the size of an irregular particles when we have equated the volume. Is this clear? This is called as volume diameter. Second, surface diameter. Have you written this? So actually this is the size of an irregular particles which is said to be as a size of an equivalent sphere. The size of an irregular particle is going to be defined in terms of size of an equivalent sphere by equating the property of volume. Now similarly, if you have any irregular particles and this is equivalent to a sphere, but here we are going to equate surface area. Surface area of particle must be equal to surface area of sphere. Surface area of sphere. Then whatever diameter is there of this equivalent, it is diameter of equivalent sphere of this irregular particle is called as ds. How can you find the ds? By equating the surface area. So let's say Sp, or you can say Sp is the surface area of the particle, let's say, and surface area of the sphere is what? Pi r square, 4 pi r square, 4 pi r, or you can say in terms of diameter, ds square by 4 pi ds square. Yes, it is clear. Then ds square, this should be Sp surface area of the particles upon pi, and ds surface diameter, this should be square root of Sp upon pi. Any problem to anyone? So this is again, it is a size of the irregular particles in terms of size of equivalent sphere when we have equated the surface area. So what is sent here, you can also write one in this figure. You can, this is called as surface diameter, ds. This is the size of an spherical, equivalent spherical particles called as ds when we have equated the surface area of the particle. This is dv. Clear? Pawan Yadav. Now third one is that, the third one is volume surface diameter. In volume surface diameter, if this is equivalent to this if volume to surface area of this particle is same as volume to surface area of the sphere, is same as sphere. The corresponding diameter is called as dvs, volume surface diameter. Then how can you calculate volume surface diameter, my dear student? The volume surface diameter is Vp upon Sp. Volume to surface area of the particle must be equal to volume to surface area of sphere, and volume of the sphere is pi by 6 into dvs cube. Why dvs? Because we are going to equate the volume surface, that's why. And here the surface area is pi into dvs square. Pi cancel here, then this become here dvs upon 6. dvs upon 6. Then correspondingly the volume surface diameter is defined as six times volume to surface area of the particles. Is this clear? And the volume surface diameter also called as Sauter diameter. Very important. Volume surface diameter also called as Sauter, S-A-U-T-E-R, Sauter diameter. Volume surface diameter is the diameter of the equivalent sphere of an irregular particles. Volume surface diameter is the diameter of equivalent sphere of an irregular particles when we have equated the volume to surface ratio. So we can define one more term here. So this is, let's say, dvs, volume surface diameter. Now then similarly surface volume diameter. Next is surface volume diameter. Surface volume diameter. In this case we should equate what? Anyone? dsv. This is surface. It is the diameter of the equivalent sphere of an irregular particles when we equate the surface to volumes Sp upon Vp of the particles should be, it is obviously pi into dsv square upon pi by 6 into dvs cube, dsv cube. Then here pi cancel, then my this one you will get as 6 into 6 upon dsv. Then dsv is found to be 6 into vp upon sp. That is volume surface volume diameter. Sauter diameter, yes. Now similarly there are various ways are there. We can define the weight diameter. What is meaning of weight diameter? By equating the weight. Is this clear? So dw. So there are various ways, not only one way here. We can define here dsv. Here we can define dw by equating the weight of the particle. So for a single irregular particles there are different types of equivalent sphere diameter is there. आने तो कोई दिक्कत नहीं है, हमने तो बस डिफाइन किया हुआ है डिफरेंट. तो दिस इज ऑल अबाउट योर शेप. नाउ क्लियर अबाउट द शेप. ओके, तो दिस इज ऑल अबाउट योर sizes. So how can define the size of an Martin diameter? And Farad diameter has its own drawback. That's why we should go for the another concept that can be used anywhere, and that is called as equivalent diameter of an equivalent sphere for an irregular particles. Equivalent means कि when we are going to assign the size or diameter to an irregular particle that is same as the diameter of the sphere, when both are exposed to the same process, its behavior must be same. That is called as equivalency. Okay, so depending upon the process which diameter we should consider, the question should be that which diameter we should consider, and in which condition we should consider the volume surface diameter, in which condition we should go for surface volume diameter, in which condition we should go for the surface diameter, in which condition we should go for the volume diameter. It's totally depend upon the applications. It's totally depend upon the application. For example, if, listen my dear student, surface and volume and surface, you can say surface to volume ratio diameter or surface volume. For example, let's say my dear student, volume diameter is only important. Volume diameter will be important in the terminal settling velocities applications, because if the, I've told you, if the volume of the particle is same as volume of the sphere in this case, and density is same, let's say, then mass will also be same, then both particles will have same terminal settling velocity. Okay, so obviously if we are dealing with the, because behavior must be same, I've told you, then behavior in what sense? Behavior will depend upon the applications, and if the application is the calculation of terminal settling velocities, then in this case you should use the volume diameter. Is this clear? For example, if suppose you are going to purchase a belt, if you are going to purchase a belt, then obviously you will not bother about your height, obviously you should bother about the circumference of your, if you are going to purchase the wristwatch, then obviously you will not bother about the diameter of your leg, obviously you will bother about the diameter of your wrist. If you are going to purchase the shoes, then obviously you will bother about the length of your feet. So depending upon what application is there, depending upon those applications, we should choose the different diameters. Is this clear? Depending upon what application is there, we should choose the different. Now, and volume to surface diameter is important when any particles, when any gas bubbles are going to rise in the, suppose if any gas bubble is going to rise in the liquid, or any liquid droplets is going to be fall into the air, in that case the two terms are very important. One is mass and other is surface area. Why? Because you do know about surface tension. Surface tension always acts between two different fluids, either liquid, two liquid having different densities should be treated as two different fluids. Liquid means called interfacial tension. So when any particles, when any solid, when any gaseous particles is going to rise through bubble, in that case we should bother about two parameter. Two parameter will play very important role. One is called as volume of these particles, and otherwise is surface area. And surface area very important because there is interfacial tension is there, or surface tension is there, which acts between the surface of the gas bubbles at the interface of the gas and liquids. Similarly, in the liquid also, when liquid is going to be bubble through the liquid pools, it is possible, then again the interfacial tension will play important role. That's why an interfacial tension again always acts at the surface area, at the surface of the particles. That's why the surface to volume ratio is important. Is this clear? Yes or no? So depending upon what application is there, we should choose the different diameters. Am I right? Bolo. Now if we are dealing with the catalyst, in the catalyst which are important, surface area or volume? In gravitational free settling we have to use the volume diameter. In catalyst we should go for the surface diameter. In dynamics of the gas bubble, in liquids we should go for the shorter diameter, or called as volume surface diameter. So depending upon the application we should choose the different diameters. Clear? Now this is all about sizes. So how can define the size of an irregular particles? It is clear. So always will define the size of an irregular particles in terms of size of equivalent sphere. So not only volume, it depend upon what application is there, we should choose the different equivalent sizes of spheres. For single irregular particles, different sizes of the spherical particles are there. Now come to the next topic, that is called as shape of irregular particles. We have defined the sizes. Now to define the shape of the particles, we have a two very important term, that is called as sphericity. First is called as sphericity, and the second is called as volume shape factor. Volume shape factor. The two terms are very important to define the shape of an irregular particles. First is called as sphericity, okay, and notation is called as phi s, and volume shape factor, that is called as small a, volume shape factor. Two terms are very important to define the shape of an irregular particle. How can define the sphere here, sphericity here? Please define the sphericity first. My dear student, sphericity is a measure of, as I told you, sphere is a the simplest shape of the particles because of its symmetry, and we can define the shape of an irregular particles by measuring the reference as a sphere. Shape of the sphere should be taken as a reference, कि any particles how close it resemble, how close sphericity is a measure of what is the physical significance of sphericity. Sphericity is a measure of how any particles closely resembles to a sphere, how close any particle is to the sphere, that is called as sphericity. If the sphericity is 1, it means the particles is exactly like a sphere or particle is spherical in the shape. And if the sphericity is tending towards 0, it means the particles are highly irregular in the shape. It means its shape is largely deviate from being a sphere. Okay, so if we are going to consider, my dear student, the value of sphericity phi s, its range is 0 to 1. 0 to 1, although it can never be 0, but still more than 0 or less than or equal to 1, or sometimes you can say 0, but actually not 0 practically. 0 means the particles are highly irregular in the shape. Means if the value of sphericity is going to be tends towards 0, not exactly 0, tends towards 0, it means the particles are highly irregular in the shape. Now, and if the sphericity is tending towards 1, it means the particles are going to be resembles like a sphere. Okay, so if it's very simple application I'm going to discuss here. If first of all I will define the sphericity. First of all, define sphericity is defined as sphericity phi s is defined as, please write down, sphericity is defined as the ratio of surface area of the particle, surface area of particles having same volume, surface area of spherical particle, sorry, please, surface area of spherical particle, please write down. Sphericity phi s is defined as ratio of surface area of spherical particle, defined as a ratio of surface area of spherical particle having same volume as of the particle, having same volume as of the particle, My dear student, what does it means? Means defined as the ratio of surface area of the particle. How can define the surface area of particles? It is surface area of the spherical particle, but that particle will have equal diameter. Means what diameter they are going to talk about here? For which diameter they are going to talking about here? Defined as the ratio of surface area of the spherical particle having same volume as of this particle to the surface area of the particle, Anyone? Yes, it's very simple, my dear student. So as far as surface diameter is concerned or sphericity is concerned, it's is ratio of two surface area. One is surface area of the spherical particle to the surface area of the, it is surface area of the spherical particle, surface area of spherical particle to the surface area of particle, for which we have to find out the sphericity. And surface area of the spherical particle is what? Anyone? By equating the volume, it means that is what? Pi into dv square upon surface area of the particle, that is called as sphericity. That's it. Any problem? And how can find the dv? You know very well. Pi into dv square upon sp. Pi into dv square upon sp. So it is surface area of the spherical particle. It is surface area of the particle having equivalent volume of the sphere. Clear hai? So it is surface area of the spherical particle having the volume is same as the volume of the particle to the surface area of the particles. Clear hai? Yes or no? How can you find the dV? Anyone? How can you find the dV? My son, dV we can calculate by yes. You know how can you find the volume diameter? Volume diameter of any irregular particles we can calculate by equating the volume of the sphere. Yes, very good. Now, for example, can you calculate? Please read one question. Calculate the sphericity of an cube having calculate sphericity of cube having size A, having side A. Calculate the sphericity of the cube having size A. A is the size of one side of the one side is A. How can you find this? Anyone? As you know, first of all, surface area of the cube particle, that is what, 6 into A square. Am I right? This surface area of the cube particle. Now, how can you find the dV? dV I can calculate here by equating the volume of the particle. The volume of the particle should be equal to volume of the sphere, that is pi by 6 into dV cube. And the volume of the particle is, since volume of the particle is cube, that should be what? A cube. This should be pi by 6 into dV cube. And as you know, we should go for the pi into dV square. So first of all, you should go for the dV is equal to 6 into A cube upon pi 1 by 3. This is 6 upon pi 1 by 3 into A. I can put here as sphericity is equal to pi into dV square. So 6 upon pi 2 by 3 into A square upon surface area is 6 into A square. It is cancelled out, and you can solve for this. You will get the answer. No sir, you can't use. Never sir. I have defined in the formula, sir. How you can say? Sir, here if you go through formula definition, I have told you. I have not told you by equating the other thing. I have specify you should only equate the volume. You can never, you are not supposed to use any other property to be equal. Otherwise, I will discuss you how can you calculate surface area by knowing the number of particles also. Listen, you should not equate any other properties. Here you should only equate the dV. I have told you in the definition. That's why in the definition it is clearly mentioned to you. In the definition it is clearly mentioned. Sphericity is defined as the surface area of the spherical particle having same volume as of the particle to the surface area of the particle. Mr. Soeb, is this clear? Similarly, can you calculate for sphericity of a cylinder having length equal to diameter? Please solve. Calculate the sphericity of cylinder having length equal to diameter. So clear hai? Calculate the sphericity of the cylinder having length equal to diameter. As first of all, you should calculate the surface area of the particle, and since surface area of the cylinder is concerned, you should consider surface. If it is solid cylinder, let's say solid cylinder, then you should calculate the total surface area. And as far as surface area of the cylinder is concerned, that should be what? Plus 2 pi r square, 1 for the top. Here this surface area, and this curved surface area, pi dl plus 2 times pi into d square by 4. Am I right? 2 pi r square, then it is 2 here, and length equal diameter, then pi into d square plus pi into d square by 2, 1.5 into pi d square, or 3 by 2. This surface area of the particles, and this should be, this is surface area particle. And now we should calculate the surface area of the spherical particle, and the surface area of the spherical particle should be dv pi into dv square. and to calculate dv square we should calculate the dv first. And as far as dv is concerned, my dear student, dv should be equal to the surface area of the particle, sorry, dv volume should be equal here. Then volume of the this particle is pi into d square into L. This should be equal to pi by 6 into dv cube. Pi cancel, this should be d cube, and this d cube, L is diameter, into 6, this should be equal to dv cube. Then dv should be equal to 6 power 1 by 3 into d. Am I right? Please put here and find the sphericity. This should be 6 surface area of the sphere particle. This should be pi into dv square. So pi into d square into 6 raised to power 2 by 3 upon surface area particle should be 3 by 2 into pi into d square. Pi cancel, d square cancel. You can 6 raised to power 2 by 3 upon 1.5. Please tell me the answer. I'm sorry, this should be 4. I'm sorry for this. Yes, यहाँ से निकाल लो. I'm sorry for this. Please solve dv and put here and tell me the answer. Now, so this is called as sphericity, my dear student, and the reciprocal of sphericity is commonly called as shape factor or sometimes called as surface shape factor. Please write down here. The reciprocal of sphericity called as shape factor or surface shape factor. Now the next is volume shape factor to define the shape. So what is physical significance of sphericity? You can write the sphericity is a measure of how much the particle is close to being a sphere. Call it lambda s 1 by phi s. Karthik, Shankar, clear? Lambda s is called as surface shape factor. The last term is here to define the shape is called as volume shape factor. Write down volume shape factor. Volume shape factor. This factor is used to calculate the volume of an irregular particle. This factor is used to calculate volume of irregular particles. Volume of irregular particles. As we know that volume of a spherical particle is proportional to the cube of diameter. As we know that volume of a sphere is proportional to cube of its diameter. It means volume of the sphere is equal to pi by 6 into d cube, and if pi by 6 for similarly for irregular particles, we can say कि volume of any irregular particles we can say a into d cube, and where a is called as volume shape factor. Volume shape factor, and this a equal to what? Anyone? Pi by 6 for this a equal to pi by 6 for spherical particle. and this A is any other value for the different particles. The ones from the experiment, from the data handbook, you are able to calculate the different shape factor for different shapes and put A here, and you can find the volume. Clear? Of an irregular particles. So this is your volume shape factor. By knowing the volume shape factor that is given you in data handbook, what is the volume shape factor for different shapes, and this you can use to calculate the volume of an irregular particle. So this is all about your size and shapes of an irregular particle. As I told you, if you are dealing with the, as I told you, nearly 45% or you can say more than 45% of the chemical products are in the particulate material form, and they are of different sizes and shapes. Yes, A is just multiplied by factor. So here whatever we have defined, that is only for the single particles, single irregular particles. But the question is that in practical sense we have different varieties, wide varieties of the particle sizes are there. Okay, for example, and that is called particulate matter. Particulate material means the particles of various sizes, wide variety of sizes is called as particulate materials. So as far as particulate material is concerned, let's say you have a particles of different sizes. They are particles of different sizes. Here we should use the average diameter. I will discuss it. Don't worry for this, which diameter you should use. I have told you it depends upon the application which diameter you should use. The most widely used diameter is the volume surface mean diameter, also called as solder diameter. I will discuss later on. Surface shape factor is different thing. Surface shape factor, I told you, it is just reverse of volume shape factor. You can expand the formula, then you can see what is the meaning of this. Now listen here. Here the main application of the particulate material means the particle of wide varieties of the sizes, and various particles of different sizes is called as particulate material. So here you are seeing here particles of different sizes are there, and that's why it is very important to separate the particles of the same size. Okay, now let's say here total mass of the particle is, let's say, 10 kg. For example, total mass of the particle is 10 kg, and as I told you, success and failure of any chemical process industries will largely depend upon the particle size distribution and its handling. Its handling and its characterizations and its conversion, its processing will play very important role in the success and failure of any chemical process industries. That's why it is very important how we can handle this particulate material. And handling means here we should obviously separate the particles of the same sizes. We have to separate, we have to segregate, we have to bifurcate the particles of the different sizes. For example, let's say total mass is 10 kg, and if you are going to separate, let's say this consists of 2 kg of size d1 diameter, now 5 kg of diameter d2. Now it means out of 10 kg, 2 kg of the particle is there which have sizes of d1, means 2 kg is the mass of the particles having same sizes. Now similarly 5 kg out of 10 kg have the diameter of d2, they have same sizes. Now similarly remaining 3 kg is there of size d3. So it is very important to separate, to segregate, to screen the particles of the equal sizes. Is this clear? Yes. Sir, it is not new factor, sir. It is just reverse of surface shape factor. It is reverse of sphericity. I am not going to use the new factor. Sometimes, so here I have told you that there are particles of different sizes. Then you have to distribute the particles of the equal sizes, and that is called as PSD. What is PSD? Anyone? PSD, particle size distribution. What is meaning of PSD? Anyone? This is called as particle size distribution. It is very, very important, because I told you that success and failure of any chemical process industries will depend upon the handling, characterization of the particulate material. Sir, how to know what to find, surface shape factor or volume shape factor? it will always given to you, no need to worry for this. 10 बजे क्लास खत्म हो. Sweta madam, sir, how to know what to find surface shape factor or volume shape factor? Ma'am, always it is given to you what you have to find out, surface shape factor or volume shape factor. If they will ask for calculate surface shape factor, then you should calculate surface shape factor. If they have asked for volume shape factor, then you should go for volume shape factor. Particle size distribution means just a very correct answer has been given by Leneo. The separation of the particle that is based on the sizes into different fractions. Clear? Called as particle size distribution. And it is very, very important, my dear student, to understand the behavior of the particle. Called as particle size distribution. Means how much fraction of the particles of the same sizes or different sizes are there. That is called as particle size distribution. It is distribution of the particle, distribution of particulate material into different fractions by their sizes, they are called particle size distribution. And how can you distribute the particles of the different sizes into different fractions? By using the screen analysis, by using the screening. That is only possible if you have particulate material. It means particles of different sizes, and if you want to separate the particle of different sizes into different fractions on the behalf of their sizes, then you should use the screening technique. In the screening, there is a device called as sieve and shaker. There is a device called as SHIEVE, sieve and shaker. Have you heard about the name? How many of you have heard about the name sieve and shaker? Sieve and shaker, and that is screening equipment. In the screening, just like in a household, in a kitchen, usually we are going to separate the floors, and if any oversized particles are there, that we are going to separate out, and undersized particles going to come down. So that is called screening. So by using the screening technique, that is called screening. Screening means just segregation of the particles on the behalf of their sizes, not shape, on the behalf of their sizes. So for screening, we are going to use the sieves, and the sieves just try to understand here. They are called as sieves. Now, every sieve, actually we are going to use the standard screen sizes. So what is the screen size? What is aperture? First of all, I am going to discuss screen size or aperture size. Although there are various screens are there, the sizes or openings of the screens are generally square, but it may be also rectangular, it may be circular also, but generally we are going to use the square technique in the standard form. Okay, so here the openings are always square. The square opening is there in most of the cases. Square opening is there. And how many number of openings are there in per linear length? That is called a mesh number. The size of the screens are defined in terms of mesh. So every screen have its own mesh number. What is mesh number? Listen. Mesh number, my dear student, the sizes of the screens are defined in terms of mesh number. Please write down here. Sizes of screen openings are defined in term of mesh number. How can you define the mesh number? The mesh number is defined as number of openings per linear length, not inch. not inch, it may be length, it may be centimeter, it may be millimeter. So mesh number is defined as, write down, mesh number is defined as number of openings per linear length. Sometimes it may be defined in per linear inch, per linear centimeter. Now if we are going to define per linear inch, then what does it mean here, my dear student? Ki in 1 inch length, if length is defined as 1 inch, if let's say it is 1 inch, then how much openings are there? 1 2 3 4 5. Then if 5 openings are there in 1 inch, that is called as 5 mesh number. So depending upon, in standard Taylor screen we are going to define the length in terms of inch, okay, but in general the definition of mesh number is defined as number of openings per linear length, okay. So how many number of openings are there? For example, in 1 linear length, how much opening? Let's say it is 1 linear length is there. Just try to understand here in 1 linear length, let's say it is 1 inch is there. In 1 inch, how many openings? 1 2 3 4 5. It means mesh number is 5. So mesh number is defined as number of openings in a given linear inch. Yes, in the standard definition, as from the standard Taylor screen, as I told you, different screens are there, but we are going to use the standard Taylor screen as a reference, as universal. Throughout the world, we are going to use the standard Taylor screen, and in the standard Taylor screen, the length should be defined in terms of inch. In 1 inch, how much openings are there? That is called as mesh number. So obviously, larger the mesh number, what it means? Larger the number of openings in given inch, or in 1 inch of the length. If more openings are there, it means more will be the mesh number. Am I right? Yes or no? My dear student, more the number of openings per linear inch, more will be the mesh number, and less the size of opening. Large mesh number means large number of openings in given length of the linear length, and smaller the size of openings. How can you define the aperture size or size of openings, my dear student? The size of openings called as aperture size. Size of opening called as aperture size. Aperture size can be calculated as how can it calculate? The size of openings or aperture size can be calculated as aperture is opening, mesh is number of openings. Aperture is size of opening. Sir, aperture means size of opening. Let's say here, try to understand here. It is size of opening. This size is called as aperture, and number of openings per linear inch is called as mesh number. Aperture is size of openings. कितना ओपन लेंथ है, साइज ऑफ ओपनिंग इज कॉल्ड एज अपर्चर, and the number of openings per linear inch is called as mesh number. Question is, how can you calculate the size of openings or aperture size? It should be size of one mesh minus diameter of the woven wire. Aperture size, listen here, it is very important to understand, my dear student, here, because there is some diameter of the woven wires. So although you have calculated the size of, if I am going to tell you that there is 10 meshes are there, 10 mesh number, it means in one linear length, in one linear inch, there is 10 holes, 10 openings are there. Then size of one opening minus, if you want to calculate aperture size, obviously it is very simple to understand here. If in 1 inch, there 10 openings are there, means mesh number is 10. Try to understand here. If in 1 inch there is 10 centimeter, 10 openings are there, then if there is a 10 mesh number, it means the length of size of one mesh is equal to what? 1 by 10. Am I right? Size of one mesh is 1 by 10, and this should be subtracted by the diameter of the woven wire, that is called as size of opening or aperture size. So it's very simple. The size of opening should be very good. It should be 1 by m. M is the mesh number minus d. D is the diameter of woven wires. It is mesh number. So 1 by mesh number will indicate you the size of one mesh, and size of one mesh minus diameter of the woven wire will give the size of openings or aperture size. Clear hai? So my dear student, we are going to use the different types of screens, but in a standard form or throughout the worldwide, we are going to use the standard Taylor screen. D is the diameter of the woven wires. Aswarya, what is the issue in this case? As I told you, if you have 10 is there, then obviously it is the size of 1, but opening kitna hoga? Opening mein you should subtract this na. So you should subtract some part of this, half part of this and half part of this, then you will diameter ultimately. Diameter of the woven wires. Sir, in 1 by m you have, it is a size of one mesh na, but I have to calculate the size of opening, sir. It is one mesh, but it is one mesh here. Listen, it is one mesh, but at the same time some diameter is also, some space is also going to be occupied by the thickness of the woven wire. Wire has its own thickness, na? So you should subtract that total by the diameter of the woven wire. That will be the opening space or aperture. There are various types of screens are there, but always we have to use the standard screen. I don't hear. Call it American Standard Taylor screen. Heading is American Standard Taylor screen. There are some features of the American Standard Taylor screens. First is their openings are always square. There is square opening. In the Standard Taylor screen, the openings are square. Second, area of opening to the next smaller screen. Sir, not 2D. Mr. Pandey, have I written 2D here? मैंने 2D लिखा हुआ कहीं? Here a single if some diameter is there, then some part of diameter is contributed into the here and here. Then obviously we should use the half of this and half of this. Sir, it is diameter of the woven wire. D here. Just like it is average, we are going to consider it is average of, you can say not, if you are not going to consider, then you should understand it to be average, because some part here, some part here, some part here, whatever part is going to be contribute, this a single wire is going to contribute two mesh here and here also. So we should subtract some part from here, some part of here. It means whatever diameter is there on average, we should subtract from the total mesh. You will get the answer. As far as mesh is concerned, this is, as I told you, size of the mesh is here. Just try to understand here. If you have a length of 10 centimeter, 10 inch, let's say, Mr. Hanuman, if you have a length of 10 inch, in 10 inch, let's say 20 number of openings are there. 20 number of openings are there. 20 number of openings are there, then what is the size of one mesh? Can you tell me? What is the size of one mesh? 20 number of openings are there in 10 inch. Then what is mesh number? Mesh number is 120 bolo. 120. 120 number of openings are there in 10 inch. Then what is mesh number? Anupam? Charge लगाओ जल्दी से मोबाइल का. Mr. Hanuman, it should be 120 by 10. Because it is mesh number is defined as number of openings per linear inch. So 120 is there in 10. In 1 inch there is a 12. 12 is the mesh number. Okay. So what is the size of one mesh? If it is a 12 mesh in 1 inch, then size of one mesh is 1 by 12 inch. Yes or no? So 1 by 12 inch is only when we are going to consider there is no wire, no size is going to be occupied by the wire. The size of one mesh is here, but at the same time, whatever the wire through which it is going to woven, knitting, it has some sizes, some diameter. Then obviously total size is not available for the openings. Some has to be subtract, and obviously some part of this here, we have to subtract some part here, half a part. Then it become on an average we should subtract the size of mesh with the diameter of the woven wire. You will get the size of aperture. Clear hai? Are you getting my point? Mr. Somansgarg, definition is correct. Mesh number is defined as number of openings per linear length, per linear inch. Number of openings, not size of openings. Size of opening is different thing. Number of openings are different thing. Definition is correct. Mesh number is defined as number of openings per linear inch. Size of opening is different thing. Size of opening is defined as size of one mesh minus a diameter of aperture. Diameter of wire. That is called as aperture size. Clear hai? American standard Taylor screen, what property it have? It should have, first of all, the openings are square, and second, area of opening. Area of, what is area ratio? Anyone? Twice area होता है किसका? Area of opening is twice of area of next smaller screen. Next smaller screen. It means, let's say you are going to place the screens, two screens here, mesh, two screens like here. Just try to understand here. Then here, let's say it's ith screen, and here it is I plus 1 is screen, counting from top to bottom. Then area of this screen is twice of area of the next smaller screen. It means ai upon ai plus 1 is twice. Clear hai? Yes, very good. And if it is area, then what about the opening? Size of opening, if you have a two consecutive screens are there, and always we should place the first screen of the larger size. Then larger size means what? Larger size means a small mesh number or large mesh number. Obviously large mesh number. Large mesh number means large number of openings, and large number of openings in a given length, it means a smaller size. Clear hai? Very good. It is about area. Now next thing is that size of opening is root 2 times that of next smaller screen, that of next smaller screen. It means, let's say L is there, aperture size, then Li upon Li plus 1 should be root 2. Mesh number is large, it means opening, size of opening is small. So this is the property of standard Taylor screen. And always we are going to arrange the screens, different screens of different mesh numbers. First of all, let's say you have a 3. I'm going to draw here. Better is that I should use the Soeb. हमें टेक्नोलॉजी यूज करना चाहिए, क्या बोलते हो? Okay, let's say you have a 3 mesh. As we are going to come down, then the number of openings should be increased in a given length. It means mesh number should be increased like that here. So if you're going to place the particles, of different shapes on the first screen, then what happen? Some particles, every mesh number, every mesh has different sizes, and that is given in the handbook. For given mesh number, some sizes are there that will be given to you in the handbook. So any particles whose sizes are less than this openings, it will retained, and any particles whose sizes are equal to the size of these openings or lesser than this will come down. Okay, the some will get retained here, some will get retained here, some will get retained here, and some will come down here. Is this clear? That is called a sheave and shaker. You should place the particles on the top means you should place the particles of different sizes. You should place the mixture of the particles in the screen of lower mesh number. Let's say its mesh number is 400, then this should be 500, this should be 600. Lower mesh number means less number of openings in given length. It means openings are much larger than the 500. So any particles which are going to be, whose sizes are more than the size of this opening, they will retained, and any particles whose size are equal to the size of openings or less than, it will get come down, passing through it. And then again same is going to be happen here, and on the behalf of this we are going to collect the particles of different sizes. Means we are going to collect the fractions of different sizes. That we call as particle size distribution. And yes, we should place the particles on increasing mesh number, and we should agitate, we should shake it, called as sheave and shaker. We should agitate, and as the time for the given length of the time, and once you will be ensured that whatever separation is there that has been happened, then stop, and then you should collect the particles from the different mesh, and you can wait. So you are able to separate the particles of the different sizes in different fractions. That is called as particle size distribution. And as far as analysis of the particle size distribution is concerned, the two analysis is there. One is called as differential analysis, and other is called as cumulative analysis. Differential and cumulative. In differential analysis, or you can say in any analysis of the particle size, how can you do the particle size distribution analysis? We should, first of all, we should weight the particle. Let's say here M1, here M2, here M3 mass. Total mass, M1 mass we have collect over the first screen, M2 mass we have collect over second screen, M3 mass we have collect over third screen. Total mass is M1 plus M2 plus M3. Then can you calculate the mass fraction? Yes or no? Can you calculate mass fraction on each screen? Yes or no? Please let me know. Mass fraction on the first screen is what? Mass fraction, let's say M1 kg, M1 gram, you can say M1 gram has been collected over the first screen, M2 gram over the second, M3 gram over third, and rest on the pan. नीचे क्या होगा? Pan होगा. I will discuss in the next lecture. You can see, like in short form, I can draw in this way. Here pan is there. They are different screens. Clear? So first of all, you should put here, and there is screens are there. There is screening here. In short form, we can represent in this form. And here pan is there. Pan. So let's say M1 gram has been placed here, M2 gram has been retained on the second screen, M3 gram on third, M4 gram on the third, and M5 on the pan. Total mass is M1 plus M2 plus M3 plus M4 plus M5. Am I right? And once you know the total mass, then you can calculate the mass fraction on each M1 upon total mass, M2 upon total mass, M3 upon total mass, M4 upon total mass. Yes, very good. And once you know the mass fraction of each particles, then obviously here we can say कि this M1, this particle, whatever particle has been, my dear student, whatever particle has been retained on the second sieve, listen, what are its size range? Can you tell me? What is the minimum size range and maximum size range of the particle that has been retained on the second screen? Anyone? Any particles which has been retained on the second screen, what is the size range of the particles that has been retained on the second screen? Obviously, its size is maximum size of the particle that has been retained on the second screen is equal to the size of the opening of the first screen. And the lowest size of the particle that is retained on the second screen is the size of its own screen. Am I right? Please listen here. In second screen, on second screen, whatever the particle has been retained, it means maximum size of the particles on the second screen is equal to size of the opening of the first screen. Am I right? And the lowest size of the particles that has been written on the second screen is equal to size of the opening of its own screen. Then you can calculate the average. Whatever the m2 mass is there, you can calculate the average diameter of the particle. How can you calculate average diameter of the particles? Can you calculate? How can you calculate the average diameter of the particles on the second screen? That should be, or you can say average diameter of the particles on any screen. Average diameter of the particle in ith screen we can calculate by diameter of the particles, or you can say size of the particle, size of the openings, size of the openings of I minus 1th, means before that, plus size of that mesh by 2. Is this clear? If you want to calculate the size of average size of the particles on any ith screen, then that should be the size of openings, size of openings before that screen plus size of that screen by 2. It's average. Now m1 is more than m2 more than m3. It is not necessarily. It depends upon, you can't say, it depends upon what sizes we have considered. It is not necessary that m1 is more than m2 than m3. Anything is possible. So average size of the particles retained on any screen is equal to where di minus 1, let us know where di minus 1 is the size of opening, size of opening of I minus 1th screen, means before that screen, and di is the size of opening of ith screen. And you can calculate average size of the particle that has been retained. Now my dear student, you know the fraction. Can you draw the plot between the mass fraction and average size of the particles? Can you calculate? Yes or no? From this experiment, can you have a data about mass fractions and, or better is that, mass fraction retained? Can you have mass fraction retained? Very important, retained. Mass fraction retained versus average diameter of the particle. Can you have? Yes or no? Mass fraction versus average diameter of the particle. Yes, obviously. Navya, size of the screen first is more than size of screen of the second, but you can't say about the mass now. If all particles are very small in size of the size of the first mesh, then all will be come down, no one will be retained. For example, Navya, try to understand. Let's say you first screen, second screen. First screen have size of, let's say d1 is given as 20 micrometer, and here d2 is given as, let's say it is 10 micrometer. And if you are going to place the particles, and maximum particle size in this mixture is of 15 micrometer, then obviously what happened? No one will be retained on the first. Mass fraction retained on the particle on the first screen will be 0. All will be passing through, because maximum size of the particle in the mixture is only 15 micrometer. Then no one will be retained on the first screen. If the size of the first mesh screen is 20 micrometer and second is 10 micrometer, because mesh number increases, size will get decreases. Then if you have a mixture of the particles, and the maximum size of the particles in the mixture is 15 micrometer, then no one will be retained on the first. All will pass through the first and get retained on the second. Clear? Hai? Now my dear student, so can you, from this experiment, can you have a data between mass fraction of the particles retained and average particle size? Is this clear? Can you have a data between the mass fraction retained and the average particle size? And how can you calculate the average particle size? I have told you. Average particle size on any screen you can calculate by taking the average of size of the openings of before that screen plus size of the opening of that screen by 2. It's average. Then yes, obviously, if you're going to plot, this is called as mass fraction versus di, diameter. Then obviously mass fraction versus diameter of the particle. What types of shape is there? Obviously you should know, my dear student, the particles which have larger size will have a small mass fraction that will be retained, because there is a maximum possibility that yes, it will be like a bar graph. Okay, so how the shape is there? Is it shaped like that? It should be, it may be, because it may be possible that at the last this is continuous function is there. This may be the chart you can see by the experiment, because here if the particle size is large, then no mass fraction is there. Again it get increases and reach to the maximum at some certain sizes, then again it will drop to, and it is not necessary that it will start from here, it may be also start from here. It depends upon the what figure we are going to, what material we have chosen. Is this clear? How can find the average diameter on the top? That I will discuss in the next lecture. How can you find the average diameter on the pan particles that has been collected on the pan? That I will discuss in the next lecture. Clear hai? Up to this point, any doubt you have? So guys, thank you so much for today. If you have any doubt regarding up to this class, please give me, please tell me if it's there. Otherwise I will continue by tomorrow. एकदम पैनिक हो जाते तुम लोग यार. Okay, thank you so much.